New online avatar. Before I pass the mic on to Urvashi, who will be doing the honors today, I would like to, well, a big thank you to Sridhar for getting this, the colloquium off the ground. And many thanks also to Mamta for her help with, her immaculate help with planning the logistics. And of course, a big thank you to my co-conveners, Urvashi from LAM, Deepbendu from Theoretical Physics, and Vikram Rana from Astronomy and Astrophysics for their enthusiastic help in, getting these colloquia off to a flying start. So Urvashi, over to you.
Thanks, Ranjini. Yes, it's very, very exciting to start this colloquium series. And then we have this new online avatar. And we can already see the benefits of that because we have various time zones already represented in the people we have admitted. So, but then of course, it is actually very, very exciting because we have Gregor Weihs as our first speaker for the RRI online version of the colloquium series. Gregor, of course, has been a friend, collaborator, and mentor in different orders for the last, 15 years. So it is even double the joy to have him as the first speaker. So I will actually give a short introduction to Gregor. I'm sure not many people need it, but then, for the record. So Gregor Weihs is a professor of photonics at the Institute for Experimental Physics at the University of Innsbruck and interim president of the Austrian Science Fund, FWF. He received his MSc degree from Innsbruck University in 1994. His PhD degree was from Vienna University and it was awarded sub auspices precedentis. And I'm sure that means that it was great, by the president of the Austrian Republic in 2000. Before returning to Innsbruck, he held a junior faculty position at the University of Vienna, was consulting assistant professor at Stanford University and associate professor at the University of Waterloo, Canada, where he was awarded the Canada Research Chair in Quantum Photonics. Other major awards include a starting grant by the European Research Council and the Wilhelm Exner Medal. He was a member of the Young Academy of the Austrian Academy of Sciences and a fellow in the QIP program of the Canadian Institute for Advanced Research. His research interests include fundamental physics, quantum and semiconductor optics, and quantum information. So with that, I won't take any further time because this colloquium is something we have been really looking forward to, and I'm sure it will be extraordinary with the extraordinary claims that require extraordinary evidence, closing loopholes in Bell's inequality experiments. Over to you, Gregor.
Thank you very much, Urvashi. I hope everyone can hear me well. If not, please let me know. And it's a great pleasure for me to give this colloquium. Also, thank you very much to Urvashi and all the organizers for inviting me in these times. In fact, I've today just come out of quarantine after a COVID infection, which was extremely light, but still gives me authority certified immunity, which is probably as good as a vaccination for the time being. But today I'm back in the office actually, and we'll be speaking about things that are in part old, but there will be something new at the end. I entitled this "Extraordinary Claims Require Extraordinary Evidence," and it does turn out that after, well, it's now what, 60 years of experimentation on Bell's inequality, you will still find people, and I'm not talking about lay persons, but I'm talking about physicists who will deny the non-locality entailed by entanglement and claim that there must be some other cause for this correlation that we're observing. And so the story of Bell tests or Bell's inequality experiment has been one of closing loopholes, finding loopholes and then trying to close them. And as you will see, a lot of this is really about technology, and technology takes time and money and people to develop. This is the story. But I'll start some long time back with, and this is my motivation. So I was 16 years old and a bit of a nerd at the time. So I had a subscription to the Scientific American, or the German version of it actually. And there was an article by Abner Shimoni entitled The Reality of the Quantum World. And I read this and I talked to my physics teachers in high school about it and realized that my physics teachers knew nothing, even though they were very good teachers, but they knew nothing about quantum physics, at least not this part, and certainly nothing about Bell's inequality or quantum correlations. And so it's I don't know, it's fate or a mystery of the connections in the universe that I was eventually able to do a PhD thesis on exactly this topic in my hometown of Innsbruck. And this is the main paper published in 1998 with only 5 authors at the time. And I venture that you probably know every one of them. They've all remained in quantum optics. Certainly, you know, well, they are here in order: Thomas Jennewein, Christoph Simon, Harald Weinfurt, and Anton Seilinger. And this was just the motivation. And now I'm going to give you a bit of an overview. I'm going to start very, very basic on entanglement and correlations. This is more for actually like a classroom talk, perhaps, and not or a classroom lecture, not so much a colloquium at this point. And then talk a bit about the early Bell tests and what motivated us to then do what I would call an experiment that enforced locality. And once I'm done with that, I will talk about the newer developments, the loophole-free experiments of 2015, and then some very recent work we just published, in fact, about the other end of the correlations. And that is why is quantum mechanics not stronger correlated than what we can measure in nature. All right, so let me start extremely basic for hopefully the benefit of some student audience or very unfamiliar ones. And this is in the modern language, the smallest possible quantum system has 2 states. We call it a qubit. And I always like my students to think of these as 2-component vectors of complex numbers, but simply 2-component vectors. Okay, and once we know that quantum mechanics is linear, we know that all superpositions, all combination of these vectors are equally legal states with arbitrary coefficients A and B. And the magic begins to happen when we combine systems, because now quantum mechanics tells us that multiple systems live in a tensor product Hilbert space. And so 2 qubits would be a 4-component vector, and 3 qubits would be an 8-component vector, where we begin to see the exponential growth of the Hilbert space as opposed to classical physics configuration space, which grows as the direct sum. And of course, this is at the heart of the entanglement, because now if in our 2-qubit space we construct states and then build superpositions of these states, we find that there are states like the one here, the 0, 0 plus 1, 1, not normalized here, is a 4-component vector, 1, 0, 0, 1. And obviously, or maybe not so obvious actually, you cannot write this as a tensor product itself. So this, as we call it, entangled state, does not factorize. It factorizes in no basis that you try, and it is entangled. And what fascinates me sometimes is that this is a seemingly simple mathematical property, and yet it doesn't seem to have interested mathematicians as such. This is really something that only comes from physics, as far as I know. Now, entanglement, the term, as you all know, was coined by Erwin Schrödinger. And Schrödinger, in fact, talked more about the predictions. He talked about the measurement system getting entangled with the system to be measured, so that the predictions about the system and the predictions about the apparatus become entangled. And now I also have to go back to the German version of this, because the German version, a German word that got translated into entanglement, is in fact Verschränkung, and it's more like a bracing structural link that cannot be undone without breaking something. So a much more rigid and structured connection than the English entanglement would entail. All right, and we find that in a maximally entangled state, two qubits or two particles in fact lose their individual properties completely. They only have joint properties. So we can only talk about them being the same, but we cannot talk about an individual one being 0 or 1 or any particular state by itself. To put this into more physical terms, one of the bases and systems that we do like is the photon and its polarization, with the simplest sort of basis states being horizontally and vertically polarized. And we find that if we take such an entangled state, the HH plus VV, which we often call phi plus, that if we write this in the HV basis, well, we have it already there. And then if we rewrite it in the diagonal, anti-diagonal basis, so where now our polarizers or analyzers are oriented at an angle, the state in fact looks exactly the same with the new labels. So it obviously stays entangled. If that was not a basis independent property, it would be much less interesting, or in fact, probably not interesting at all. And now let's look at what this means in terms of experiments, because a lot of entanglement physics is done nowadays with very hefty mathematics. As soon as you go to larger systems with more subsystems, things become very, very complicated. But what does it mean for me as a simple experimenter? You know, I have two apparata, and they're usually called, or their operators are called Alice and Bob. And the apparatus is a very basic machine. It has one continuous input. I would call it alpha on Alice's side, and we'll call it beta on Bob's side for suggesting an angle. And I would get either of two results, a 0 or a 1. In some cases, it's a -1 or a +1, but it doesn't really matter how we label our results. And now if we the events we measure on these machines could originate from some kind of source, but for the purpose of this measurement here, it doesn't really matter whether they originate from some source or have been planted in the devices before. And so now when we measure and we see, say, on both sides, we see the red light up, so that that's a 1 on both sides, we would say the results are positively correlated. If we get opposite results, a 1 and a 0, we would call it an anti-correlation, negative correlation. And obviously then if we do this many times and average, we would get an average correlation. If it's perfectly correlated, it would be all +1. If it's perfectly anti-correlated, the products would all be -1, or the correlations. And when it's 0, then there is no correlation, meaning that a measurement on one side has no connection to a particular outcome on the other side. And now for further analysis, we can of course do this for various settings of our input parameters, alpha and beta. So this is the correlation we find. The other thing, and this is what I said before, entangled qubits or particles in entangled states have joint properties, but they lose their individual properties. So if we were to measure only one side of the system and not know or forget about the other side, and starting with our phi plus state here, we would find that this measurement on the left side gives us a probability of 1/2 for the 0 outcome and a probability of 1/2 for the 1 outcome. And we would basically see randomly a 0 or a 1. And that's, in my experience, another fact that is very often missed by, or perhaps it's in latest depictions of the situation where people talk about the correlations, but they don't realize that the correlations come at the price of the individual outcome of being completely random. And in fact, if you take this very seriously, it immediately tells you that these correlations do not allow you to signal, because no matter what happens on the other side, the results you will get, no matter how you measure, will always be half and half, 0 or 1. Okay, so that immediately tells you that proposals like the I'm sure Charlie knows this, by Nick Bennett, the superluminal communication by amplification or cloning, will not work, no matter what kind of amplifier you have. So this is what I said before, no individual properties. And now, once more, the correlation in terms of probabilities. If we list all the 4 probabilities for 0, 0 to 1, 1, we find, as expected, it's 1/2 for the 0, 0 outcome, 1/2 for the 1, 1 outcome, and the 1, 0 and 0, 1 outcomes never occur. And this is kind of important for then deriving the inequality. And this is, of course, also true in any rotated basis, as I've said before. And then finally, talking about the correlations, we also have to remember that if we do not choose bases that are parallel or orthogonal, but we choose bases that in polarization terms are rotated by 45 degrees, I guess in spin terms, they would be rotated by 90 degrees, that then the outcomes are completely random. There is no correlation. All 4 possibilities, in this case, 0D, 1D, 0A, 1A, where A and D refer to the diagonal anti-diagonal bases and 0 and 1 to the HV bases, are all equally likely, and therefore there is no correlation. So quantum correlations are strong, but they are kind of limited too, depending on our relative measurement angles. And all of this was probably obvious much earlier to some very smart people, among which I would count Einstein, Podolsky, and Rosen, of course, who then told us that even this type of non-locality, where one cannot signal, is somehow at odds with how we normally imagine the world. If we find correlation in nature, in society, there's usually two for correlation. The one is a common cause, where one thing causes both your observations, and the other one is simple straight causality, where one event causes the next, and obviously there can be correlation between these two. But without a common cause or a common or a direct chain of causality, it is hard to imagine in a classical world how there would be correlation. And so Einstein, Podolsky, and Rosen said, well, it simply cannot be that the reality on one end of the of a system, of two systems that don't interact, can influence the reality on the other side. So the measurement on one side should not be able to influence the reality on the other side. And yet they thought that it was possible to supplement quantum mechanics with hidden variables. They're not called that way in this article, so that eventually perhaps quantum mechanics could be completed, which is kind of the question they ask in the title. And people did actually attempt to prove things about hidden variables, including eminent people like John von Neumann, where the simplest function of the hidden variable would be that instead of only having a certain probability to generate an outcome for an observable A, the hidden variable would in fact determine the particular eigenvalue that you would measure for this observable. And as I said, people tried to prove that that was not possible. But in fact, one of John Bell's achievements is to show that many of these so-called no-go theorems against hidden variables all failed. So as long as we stick with sort of one single system, it's not possible to prove or to refute hidden variables. And further to this idea of hidden variables, an important picture is that of Bertelmann's socks. Reinhold Bertelmann on the right of Anton Zeilinger here. He's a high energy physicist and in fact used to share an office with John Bell at CERN. And apparently, and in fact he still does, but apparently already at the time, he always used to wear 2 different socks, never a pair. And so Bell said, well, most people believe that correlations are like Bertelmann's socks, because as soon as we see Mr. Bertelmann stride into the office and present a pink sock on one foot, we would immediately know or conclude that his other foot would not be in a pink sock. And that's a trivial classical correlation. It's sort of knowledge, prior knowledge that we have. And in fact, the value is predetermined. So obviously, Mr. Bertelmann's socks will not just choose their color whenever we happen to look at them, but in fact, they have that color all the time. And therefore, this is perhaps a trivial correlation. But Bell said is very difficult, and this is also my experience, to convince people that quantum mechanics and nature is actually different from this type of correlation. And so I guess the big achievement is really to show by John Bell that quantum correlations can be measured, and that there is a measure for them that distinguishes them from just classical correlations. That was in 1964, and we'll go through that in just a bit. But I wanted to start out with showing the correlations as a function of difference angles. So if we now manipulate in our apparatus the angles alpha and beta, we will find that for the state that I proposed before, the phi plus state, the correlation will in fact be a cosine. And to make it a little more physical, we can imagine a source that emits photon pairs, and we have analyzers, polarization analyzers at angles alpha and beta. And if we now measure our correlation as a sum of the probabilities with positive correlation minus the probabilities with anti-correlation, we get a quantity that varies between -1 and +1, and we will find that for photons, this will be a cosine of twice the difference angle between the polarizers. Cosine curve with full amplitude. And already you see here in sort of with fainter lines, other forms that this correlation, angle-dependent correlation could take. For example, it could be just a straight line, or it could be a cosine with the reduced amplitude. And either one is possible with classical physics or hidden variable, but it is not possible, as John Bell showed, to get the cosine curve with the full amplitude from hidden variables. And to see this, I will go through the derivation of the Clauser, Horn, Shimoni, and Holt inequality. Unfortunately, Mike Horn passed away, it's almost 2 years ago now, I think. And Abner Shimoni died in 2015. John Clauser and Richard Holt are still alive. Because their merit was it to make the inequalities a little more fitting to what experiments could really do. And this is also the version that is mostly used in experiments, perhaps except for the loophole-free experiments now. And so the idea is that our hidden variable lambda and the measurement function A will determine the result on the Alice side, and the same on Bob's side with B and beta. And hidden variables are any kind of object, in this case, simple real parameter over some density that makes this a measurable space. And in this case, our outcome functions simply have to be smaller than 1. So you might imagine these are the outcomes already averaged over some cases. And in fact, the outcomes can be 0 here, meaning that there was no no result at all. In fact, as one logical mistake here, these functions are supposed to be plus or minus 1, not 0 and 1 for the two results, but that's not so important. So now let's try to build this inequality. We'll take the correlation value E at two different angle settings, alpha and beta prime, and build the difference of the two. And then because A is smaller than 1, and as we put absolute bars there, we can in fact get rid of A. The inequality will still true if we replace the A here by a 1. And so we get this inequality, and we can do the same one or a similar one with a plus sign in the middle. So now that we can bound E alpha beta minus E alpha beta prime by this integral just over the B functions, and likewise with the plus in the middle. And now we observe that the sum of these two terms will always be smaller or equal than 2, because obviously if one of the absolute bar terms is 2, then the other one must be 0, and vice versa. And now with that, we've derived the Bell CH-SH inequality, which has the characteristic minus sign in one thing, in one of the two terms, but you're free to derive any other combination of signs here. All right. So what if we were to evaluate this for our quantum mechanical entangled system? What would we find? Well, we take our quantum mechanical expectation value of the correlation, which is the cosine of twice the difference angle, and now put in some particular angles, alpha, alpha prime, beta, and beta prime. And once we do this, we get this combination of cosines where the minus sign in the correlation term here is then cancelled by the fact that the cosine of this large difference angle is negative, and so we get 2 times square root of 2, and obviously this is larger than the 2 that Bell's inequality told us the correlation could be. All right, and this was obviously the status already for John Bell, who knew that nature or quantum mechanics predicted that his inequality would be violated, and so there was a quantitative test. And then people looked into this. There were so there was some data out there, but just in some other just like in some other cases, and I'm thinking of our work, Ubashi, where you think something must have been measured 1,000 times before, but it hasn't actually. Sometimes very obvious experiments have not been done. In this case, I think it was not so obvious that there would be data, and so I think the first dedicated experiment was by Stuart Friedman and John Clauser in 1972, where they looked at photon pairs or photons emitted in a cascade from calcium decay that was pumped by a lamp, submitted these photons to polarization filters, and measured them with photomultipliers, looked for the simultaneous detections, and found eventually a violation of Bell's inequality. And at that time, I want to point you to the detection rates. It was about 0.2 per second, which is in fact not so bad considering some of the multiphoton experiments nowadays, where the rates are even lower. So if there are questions in the meantime, please just post them to the chat, or even voice them over audio. I'll be fine to answer them. Experimentally, this was quite a bit improved by a series of experiments carried out by Alain Aspect, mostly because he improved the source by using a laser to pump the cascade. which also gave him better directional correlation for the emitted photon pairs. Still not perfect though. And then at some point came parametric down conversion experiments.
Gregor,
Yes,
sorry, there's a question in the chat window.
Right. So then came parametric down conversion experiments, where the now, because we're creating these photon pairs in the crystal, they're directionally correlated and can be easily caught and with much higher efficiency. There was a question about slide 21. What is the relation between angles alpha prime and alpha? Well, there's no relation. It's completely up to the experimenter to choose these angles. It just means that these are two different settings that one may do on one side. Although there's one thing, and or a frequent dispute between promoters of hidden variable theories. This is often called counterfactual, because we are combining observations from measurements that cannot be done simultaneously, because choosing one angle and choosing another angle are two things that are mutually exclusive. And so there's people denying that it even makes sense to combine these. But my answer to that is, if we cannot reason about the connections between different experiments, then why would we even do physics? You know, if you said that this makes no sense, then that every angle experiment stands only by itself, and that's a very limited view of physics and what it can predict, in my opinion. All right, so these were some early experiments, and the most obvious problem with these experiments, the most obvious loophole, I think it was, I'm not exactly sure who was the first to point it out. I only know that Philip Pearl, I think, was the first to come up with a model exploiting this loophole. Is that obviously not all photons were measured. In fact, only a very small portion of the photons emitted from the source was ever measured. And so what do you do about this? Because obviously the inequality could be true or fulfilled for the entire ensemble, whereas somehow nature conspires against us and would show us, for the reduced ensemble of detected photons, a violation of the inequality. And there's really, except maybe for arguing that why should nature be conspiratorial, there's clearly no logical implication that it would that this would be a binding result. And there's various ways of embedding efficiency into the inequality or the correlation. It's a matter of choice a little bit. One way of seeing is that if I in fact calculate the probabilities by dividing the number of detected pairs or detected events by the number of detected photons, even when there was no photon on the other side, my correlation would immediately reduce by eta squared, if eta is the efficiency or the probability of detecting a photon on one side per emitted photon. And once I do this, I see that my correlation drops like a rock, because at eta being equal to 83%, this in fact goes below 2, so you cannot violate the inequality anymore. And what's been done about this is that the interpretation of experiments has been using the so-called fair sampling assumption, where instead of dividing or normalizing every count rate by the number of detections on this side, you would only divide it by the sum of all the possible coincidences, saying the cases where you had a photon on both sides of the experiment, in which case eta drops out and your correlation can be as high as allowed by quantum mechanics. So that was the one loophole, that for sort of small systems without spatial separation was, I guess, closed in 2001 by an ion trap experiment, and in the Wineland group. And the other loophole, which I'm going to concentrate on a bit, was a so-called locality loophole. And there is a quote by Bell from 1981. So before Alain Aspect's last experiment was published, where he says, of more importance, in my opinion, is the complete absence of the vital time factor in existing experiments. The analyzers are not rotated during the flight of the particles. And so for Bell himself, this lack of locality enforcement was more severe than the fact that we're missing out on some photons. And he already points here to the fact that Alain Aspect was engaged in such an experiment. And Alain did this by building acousto-optic deflectors. So whereas an ultrasonic wave in water deflects the photons by an angle or not, depending on whether on the amplitude of that acoustic wave. And then there's two polarizers set at the fixed angles. Here we have the A and A prime corresponding to our alpha and alpha prime before, and then the detection. And this was fine. The length of the experiment was roughly 13 meters. And the one thing that was not perfect at the time is that it was not possible, I guess, at least not easily, to do this in a random fashion. So Alain Aspect basically had to run his deflectors with a periodic signal that was somehow predictable in a way, even though, of course, then hidden variables conforming to this these predicted settings would be a little more involved, and they would not be completely independent. But still, and in fact, this is a quote from Abner Shimoni, but also Anton Zeilinger wrote a little paper finding a funny resonance with the modulation frequency and the separation between the experiment stations. He never considered this very serious. He just found it a fun fact. And so this is how Anton, who was always interested in foundational experiments, came up with the idea to do an actual local experiment with random switching. It seems that at this time when we started this was 1994, 95, the time was just about right to do that in terms of the available technology. And one of the most important things was the new source we had at the time. So now I'm going to talk a bit about this experiment that was published in 1998. As I said, the new source was important, but we did build all the elements required, random number generators. We took the long distance so that now it would be possible to select the setting at a time so that the other side of the experiment would not be able to know. And what I mean here is that if these funny little arrows here correspond to all the processes that are involved in choosing a measurement, meaning sort of rolling the dice to generate a random number, generating a signal from this random bit that could actually drive an electro-optic modulator, waiting for this modulator to achieve its voltage, and detecting the photon, and in fact recording it in the computer, not on the hard drive though. If I take all this time together, that would be the little arrow here, or this bar. And now if I go back from the detection time, I can sort of exclude. I can basically say that that no influence can come from somewhere else. We will talk later about the freedom of choice loophole, which with this setup we cannot exclude. Most importantly, being that the source itself has no way of influencing these measurements, although No, that's actually not true here. That's the problem, right? If we take the forward light cone from the source, that could in fact influence our random number generator if that random number generator is somehow determined by outside things that we don't know. But in any case, the other side will not know about the setting of this at all. You know, it would have to be somewhere far back there, far in the past, so that Bob's side would know which measurement Alice would choose, and vice versa. All right, and in fact, to do this, given we didn't know at the time how fast this random number generation would be, so we picked the most remote locations we could find on our campus. In fact, this is the campus I'm giving this talk from right now. Still doesn't, it looks a bit different now, but not too much. And doing this, it was obvious that we would not do it through free space, but actually run the photons through optical fibers, which in fact is why on the space-time diagram, the photons are much slower than the speed of light. You know, the speed of light is supposed to be a 45-degree line, whereas the photons are, well, in the fiber, they travel at 2/3 the speed of light. And then also the fiber doesn't really go straight. You can see here on the map, the actual fiber path, which I measured out with the ruler and tape measure, so that we could be sure how far the actual distance was. And so here was our Alice and Bob, separated by about 355 meters, roughly 1 point something microseconds. So Aninda asks the questions, if you're using fibers, why not loop them up so that they take a longer path? In fact, the fibers were looped up because we bought 500 meters of fiber twice. So some of the fiber was looped up, and it was looped up near the source. But it doesn't really help, because what we compare in our space-time diagram is really the sort of, if we go back from the recording, if we go back by the light cone, this is the actual vacuum speed of light cone, then this is the maximum time available we have to choose the measurement. Okay, from up here to where the backward light cone intersects Alice's world line. And so it doesn't really help. Looping the fiber basically means that we move the source down here on in our space-time diagram, but it doesn't change any of the ordering itself. I hope that was understandable. Otherwise, I'm happy to discuss it more at the end. All right. So this is a drawing of the entire system. I will say a little bit about the source. Then there's the fibers. There was a question about polarization control, and at the end, so-called electro-optic modulators driven by a random number generator. And then another innovation, really, that was very different from all previous experiments, is that we actually locally recorded the photons. There was no coincidence electronics. There was no other cables in between here. And in fact, there was one physicist from Denmark, I don't exactly remember his name, unfortunately, who came while I was still doing this experiment and said, you know, what disturbs me really about this experiment is that there's always kind of a common, eventually the measurement's only done on a common location sometime later. And I said, but not so in my experiment. You know, I really record them there, and do the correlation in software afterwards. And then he was very surprised on the one hand that his concern had already been solved. On the other hand, he was also very relaxed, because he said, oh yes, this is how it should have been done all along. Except of course that experimentally it was not so easy to do that. It was kind of at the edge of what we could afford. I already showed this picture. It's not so important. The source we used was a spontaneous parametric down conversion source, and you've heard about these probably many times, so I'll be quick. We split blue photons into pairs of red photons, and because this is a volume interaction, the angular correlation between the two emitted photons is almost perfect, meaning that we can, when we have one photon, the probability to collect the other one is almost arbitrarily high. To detect it, of course, is a question of how good your detectors are. and this is the one that we used, invented by Paul Kwiat in our lab, in fact, in 1995. I was a master's student then, which has the nice property that it gives you polarization entanglement directly without any interferometer or extra mirrors. You do need some compensation crystals, but that's that. And the count rates compared to the atomic physics experiments were gigantic. Huh? So it was not a problem to have a few 10,000 pairs per second detected. And I have a photo here, one of these first sources that we built, and that in fact was the one that was sort of in the middle of the campus in an old boiler room, very unstable environment, but it worked magically. What was perhaps a bit more innovative was building a random number generator with a beam splitter and a little LED light source and two little photomultiplier tubes, so that a transmitted photon would be a 0 and a reflected photon would be a 1. And then some circuitry, also homemade, to turn this into a bit stream. One problem was that it was not so easy without, we should have had some entropy von Neumann sampling here at the end, but didn't really have the resources to build that. So we kind of had to tweak it a little bit to be balanced. The quality measure at the time for me was the autocorrelation time. So how much memory does the system have? Because that kind of determined how long I had to wait for a number to be an independent random number. And if I plot these autocorrelation traces, we see that within a few 10 nanoseconds fell away completely. We also did some entropy tests on the, if you build a byte, an 8-bit string from these bits, how are they distributed? And I mean, it's not perfect, but it's according to most of the tests we performed, it was a fine random number generator. And then the trickiest bit, in fact, was sorry, I got ahead of myself, was how to actually change the polarization basis. Obviously, you can never rotate mechanically a polarizer in some microseconds. So we use an electro-optic modulator, something like a Pockels cell, where applying electric field makes the crystal birefringent and therefore turns the polarization. And these things could run at up to 30 megahertz with sort of transition edges of 10 nanoseconds, which is kind of at the edge. And one of the difficulties is these are very difficult to align, and also the 0 point, something that we constantly had to track, which was really a bit tedious. But these work reasonably well, in fact, so I'll skip over this because time is running out, I see. And what I'm also proud of, I in fact built a completely networked control software for it, where I had sort of one computer that could control the remote computers that did the recording, but while they were recording, they were running completely offline. One important thing being that for the data collection, in fact, I had little atomic clocks, rubidium atomic clocks, so that the time bases could run completely independently and would only be synchronized by an initial laser pulse that I sent out from the center. The stability of the atomic clocks, however, was not so good, so that after a few minutes, the time histogram would spread out a bit. Here it's still roughly Gaussian with the time resolution of the recording hardware, and then as we waited longer, we would see these drift apart and need resynchronization. In any case, even with the fast switching, we got very, very good correlation curves. So these are the probabilities, or the unnormalized probabilities, and eventually measured on the Easter Sunday of 1998. That was the most quiet day when nobody was around. We got some very good values at this time. So we measured our Bell parameter at 2.73, and that being with the uncertainty here being something like 30 standard deviations. At that time, we did not calculate so-called p-values, but that's probably not so important. And one of the learnings of one of the things we did that was kind of unprecedented or unusual at the time, at least in our domain, is that we, in fact, published the original raw data on the internet. Now that URL, I think, does not exist anymore, but the data is still available, and it turns out that many people looked into these data. Tried to see whether they could get local realistic models for them. And of course it does work, because the efficiency of the experiment per site is only 5%. So clearly you can build a model, you can exploit time, or you can exploit the efficiency. That's not the problem. So from these data, quite a few papers ensued, looking for various things, and it was interesting because people really found out things about this experiment that we had never considered. For example, there was some funny variant. We found a reflection on there was some kind of reflection on one of the cables, on one of the RF cables that transmitted the detector signal, giving a spurious second peak in the coincidence time histogram, which in fact is almost the same reason why the neutrinos were superluminal initially. This was also a bad connection in Gran Sasso, and something, so that once people look at this very carefully, you can find all kinds of little dirt, but it doesn't really change, in my point of view, the overall conclusion. Okay, so this was 1998, 23 years ago, almost. And now let's look at, for the last, well, I'm already talking for a long time now, at what happened since, and I will only pick out a few things because many things happened. The one thing that this experiment of mine did not cover was the so-called freedom of choice loophole, and that meaning that in my experiment, the random number generation was always in the forward light cone of the source. So if you imagine that the source, or whatever device there is, has some control over the settings that are being generated at the ends, then the experiment it only shows that there's some kind of correlation between these devices, but not the actual non-locality. And so it was I think the first, if I'm not mistaken, the first experiment to ever consider this was done by Thomas Scheidel, the Zeilinger group. And so what you do is you take the random number generators and you move them even farther out from the experiment, so that their signals only encounter are only set at the measurement stations at a certain point in time and space, so that the forward light cones from the source will only hit whenever the measurement is done, and not earlier. And so this is what they did in one of the many experiments that were done between the Canary Islands of La Palma and Tenerife. I'm not going to go into much detail there. It's basically random number generators spatially separated from the measurement stations, so that you would get this separation. This is also sometimes called the statistical independence assumption, that goes into Bell's inequality, where you assume that the settings are statistically independent of the hidden variables, which obviously, since we don't have access to the hidden variables, is difficult to prove directly. And then I guess the really next big thing was the series of loophole-free experiments in 2015, starting with the experiment by in Ronald Hanson's group, Hansen and others in Delft. And then a bit later, in terms of publication, were Justina and others in the Zeilinger group in Vienna, and Christa Schalm in Boulder, Colorado. And I'm just gonna be very, very quick here. In Delft, they used nitrogen vacancy centers and created entanglement by measuring photons emitted from these NV center spins, thus entangle with the spins. And when you measure the photons, eventually you entangle the two remote spins. And once you know that you have this, you can take all the time in the world to measure them. Of course, the random number generation and such all have to run in the same way. This is very nice because the measurement efficiency is basically perfect. The NV center does not go away. And the downside is that the event rate is extremely low. So I think they basically had 200 and something events in 18 days. So it was very difficult to generate a lot of statistics, but in any case, I think the result is clear. Much more in line with these optical experiments I talked about before was the one in Vienna. They used the so-called Sagnac source that I'm going to show in just a bit too, generating non-maximally entangled states. It turns out with non-maximally entangled states, one can actually lower the required efficiency of the experiment, basically bias the results a bit towards where it's good for violation, which is allowed, it's legal. They use so-called transition edge sensor detectors, superconducting detectors that are extremely efficient, but also rather slow in recovering. And yet, of course, much faster than preparing the NV centers in Delft. And they could show a clear violation of the inequality with and reject local hidden variables with a really super tiny remaining sort of error probability. And this was done in the basement of the Vienna Imperial Castle to add a bit of grandeur to the experiment, perhaps. All right, and then the third one was by Christa Schalm in Boulder, Colorado. In this case, the detectors were superconducting nanowire detectors that have now become very popular and are present in all the labs that can afford them. Also a down conversion source, in fact, a very specially constructed source, where the difficulty, of course, is that in the entire chain from generation of photons through fibers to the end polarization switching, you have to really work hard to save every % of efficiency and reduce every % of inefficiency. Otherwise, it would be very difficult to get a decisive result. And same there, somehow the p-values are listed in there for the rejection. And then finally, the last thing that I guess happened in this front is that even if you place the random number generators away from the experimental stations, this means, of course, that the common past of all these devices, which is maybe a few seconds back from your normal experiment, can in fact influence the entire result. And if you believe in some form of super determinism that the entire experimental region, space-time region, influences the outcome, then maybe you're not surprised about the correlations. And in these experiments by Anton Zeilinger's group, together with MIT people, and also by Jianwei Pan's group, they in fact used light of very distant astronomical objects as the source of randomness. And now, because these now basically you limit the common path of these two sources is very small. It's only the intersection of the red and blue light cones there. So you could say that most of the universe's life could not have influenced your measurement result or your measurement setting. And so you argue that now superdeterminism has been pushed back to, I don't know, almost the Big Bang or so. I don't know if it's a matter of taste, whether you care about this or not. Obviously, in this universe, we will not be able to rule out that everything is predetermined by the Big Bang, you know. And if you believe in that, then maybe these experiments don't mean anything to you. All right, and now I'm already talking for 55 minutes, so I should be quick. I wanted to show that there's still some work in this domain beyond these Bell inequality tests, and that is the other end of the correlations, the so-called zeros and bound. So we find that our correlation that we measure, our S parameter, should be smaller than 2 for local hidden variables, but there's also a bound for quantum mechanical systems, for bipartite systems, and that is 2 times square root of 2. So Zerosen proved in 1980, it's relatively simple operator algebra, that this must always be smaller than 2 root 2. And up until a few years ago, there were really no good experimental tests to show whether that was the case or not. And it is interesting to know that, sorry, I was a bit slow here with my clicking, that Popescu and Röhrlich showed that even that a hypothetical box, PR box is called, that still cannot transmit a signal, will in fact be able to achieve 4 for this correlation, but in nature we never find 4. And in fact they formulated this as a challenge. You know, can anyone find the principle or a reason why this should be so? And many attempts have been made. The one that appeals most to me is the idea that information causality, that is, that if Alice transmits to Bob a certain number of bits, then Bob should not be able to learn more than these bits. And from this principle, these authors could sort of derive the Zerosen bound. But how well is this known experimentally? And in fact, it's not so well known, but I'll show you in just a bit. So for this, we used a so-called Sagnac source, as also used in some of the loophole-free experiments. Now we have a down conversion crystal. In this case, we get entanglement between the clockwise and counterclockwise conversion directions here. So photon pairs happen this way or the other way around. And then with this beam splitter here, you in fact construct a polarization entangled state that can have extremely high quality. And so I had the student who took basically a year to calibrate every polarizer wave plate and try to figure out all the possible errors that can happen. And in the end, measured the Bell parameter in this with this source. And here you see the difference. So this is 2 square root 2 minus the measured S. So our measured S is always smaller, except for fluctuations. You know, it can be on the other side, always a little bit smaller than the 2 square root 2. And if we average over all these measurements, we find that the difference to the Zerosen bound is some 5 times 10 to the minus 3. And in terms of fidelity of this state to the Bell state, it's 0.997, and the concurrence, the measure of entanglement, is 0.995. So this is as close as we could get with this experiment. And more interesting is, how does this do in comparison with other work? There have been some experiments who've done better. One is from Paul Kwiat's group, and the other one from Christian Kurzsiefer's group, not with Sagnac source, but with cone sources that have gone lower, in part with larger error bars, though, because once you make the entanglement quality so good, usually the count rate goes down. Whereas, and here we plot the count rate on the horizontal axis, also in a logarithmic way. So our experiment was here. So we were able to achieve extremely high fidelity and Bell parameter at a still very, very high rate of photon pair generation and collection. And this was just published earlier this year. All right, that was it. That was to show that there's still work going on, perhaps not in Bell inequality itself, but in other things. And I should also say, and this brings me to my conclusions, that I think the Bell tests are settled and the local hidden variables have been ruled out. But I also know that every few weeks I will get email from someone who has a new idea and has found a new loophole and has found a new way to sort of create quantum correlations locally with hidden variables, some form of hidden variables. And what do I usually do? I tell these people, try to program it, make software that runs on 2 computers, where I can supply random settings. They have to output zeros and ones, or minus ones and plus ones, I don't care. And I calculate the correlation. And if your software can do that, then I'll be interested. And it turns out they never do, because as soon as someone starts to program, they find what the problem is. You know, where did you actually violate any of the conditions that go into Bell's inequality? It's either the efficiency or it's the locality. And that's that. And the other thing is that the Zerelson bound, I think, is still holds some mysteries. I think it's not settled as to why nature is so. So I think this is an interesting area for future research. And here's a hopelessly outdated actual physical presence photo of my group, but most of the people are still in the group, so we're fine. Thank you very much for your attention. That was quite a bit over time, but I still have time for questions.
Yes, so thanks a lot, Gregor. I must say it's a cliche, but then it was an extraordinary talk, as was predicted in the beginning. So now we are open for questions. We have, well, we have a hand raised, but do you want to see the chat window first? Because I think there is somebody.
Yes.
Yeah.
There's one from
Abhilash.
Abhilash.
Yes.
In the classical Newtonian world, which I guess is super deterministic. That's a good question. I don't know. Everything is determined. There is no possibility to choose true random basis. So do loophole-free experiments with the possibility of Newtonian kind of theory? I think I don't know if that's 2 different kinds of determinism, because I always thought that the super determinism in the Descartes or Newton universe was kind of relaxed by chaos. I don't know if people agree with that, but that's saying that in chaotic systems, phase space diverges even for because initial conditions are never perfectly determined. So if I guess. And I would say that this is a different type of determinism than the one we have to consider for these hidden variables. But perhaps that's a bit too philosophical for me. Perhaps there are other experts who can weigh in on that. Exactly, but then the second part of the question is that Einstein really didn't like the idea of there being true randomness, and in fact, I have to say, you know, I think it's hard for people to believe in true randomness, but somehow once you've done these experiments a long time, I think you become a believer. But yeah, that's why all our students here actually do this in a lab course. In the master's program, they have a lab course experiment on Bell's inequality, and it's an eye-opener for many of them. Charlie raised his hand. There was a question also before from Aninda who asks, how would gravity affect how close you can go to the Zerelson bound? That's a very good question. I have no idea. I would have to ask Czeslaw Bruckner, who's been studying gravitational effects in sort of regular quantum mechanics, not necessarily in the true quantum gravity sense. I guess as long as we're dealing with massless photons, gravity really plays no role in our experiments. But maybe that's just maybe that's also just because because we don't have that exquisite precision to see any of that. You know, we would see the deflection maybe of photons due to gravitational fields in the vicinity, but since everything is done in labs where gravity is basically homogeneous, it would be very difficult to see that. Other people to ask would be Yvette Fuentes, I think, has been looking into gravitational effects quite a bit. I don't know if that was sufficient. Charlie?
Yeah.
Oh, I was going to say, speaking on the subject of believers, the fact that you did these experiments on Easter Sunday probably means that if God doesn't want to play dice, well, I don't know how to finish that joke, but I mean, you're introducing an element of you're pretty much bias in terms of belief. But I had a more serious comment, which was that which I put at length into the chat, but I can make it shorter, which is that already with the problem that of the using a periodic signal instead of a random signal, you've opened the can of worms that is, I think, is already the same can of worms that comes from the superdeterminism loophole, because even these cosmologically separated sources, according to inflation, which seems to be pretty well established, were once in contact. So there's no way of getting away from that. And I don't think even the idea that there's a subtle periodicity in these photons know that one of your random number one of your pseudo random number generators has a period of 37 and the other one has a period of 91 or something. There doesn't seem to me much difference in degree of implausibility, and I think that would also occur in what you said about Newtonian mechanics and chaos. If you're willing to believe that these two mutually no common factor between the period of these two periodic streams that Espay and Alt and company used, then you might as well believe that the initial conditions of the Newtonian universe were set up in order to make everybody believe that Bell's inequality was violated when it wasn't.
Obviously, I agree. Yes, it's very difficult to argue. You know, Dipankar Home has his hand
Yes.
raised. I think
Yes.
in the yes, please.
Professor Home?
I thought I heard something.
Yes, can you
Yes.
hear me? Can you
Yes.
hear me? Yes.
Yes, yes.
So Gregor, first of all, thank you very much for the very lucid and for the lucid talk with very incisive remarks. Now, a couple of comments. First of all, can you say a little more about because the type of random number generator that was used in all those 3 experiments of 2015, those are all the same random number generator based on the spontaneous emission, and that strict condition about the random generation being within a small time compared to the lifetime window. And how does that compare with the random number generator you had used in some technical crucial specificities? So this is the first question.
Maybe I'll answer that first.
Yes, yes.
That is, so in the 2015 experiments, interestingly, the random number generators all came from ICFO, Barcelona, Institute for Photonic Sciences, from Valerio Pruneri and Morgan Mitchell, I think. And there's basically laser noise that is used to generate random bits. One special thing was that in Boulder they combined this with other sources of randomness, including human created art and texts as sources of noise. And all of this became even bigger in the so-called Big Bell test, which I think was published in 2018, where many people and groups were involved, and people could put in, could basically input human randomness into the thing. But other than that, I think not much changed actually from I mean, my design was much simpler than the ICFO one. In that sense, it's the random number generators are better now, much better characterized. But I think the principle remains a similar one.
And about that issue of the generation of time within a time slot smaller than the light time, that those random number, that random number generator, say it is of 36 nanoseconds or so. So how was it in your random number generator?
Yes, well, so in our experiment, there was not really a lifetime, right?
Okay,
because the important time that we compared to would be the speed of light time between the end stations, which is roughly 1.2 microseconds in our case. And compared to that, or the autocorrelation time of the randomness generator was only a few 10 nanoseconds. So a factor of almost 100 between them, or let's say 10 to be safe. And in that sense, maybe you could say that it was independent. But as Charlie pointed out, for believers in superdeterminism or even local determinism, that's probably not an argument.
Okay. And another point I'd like to just say about the last experiment you mentioned regarding using the testing the information causality aspect of the Cyrilson bound. So after that 2009 Pawlowski paper you quoted, there was some work pointing out counterexamples to information causality. For example, the 2011 PRL paper and so on. So have you taken them in your this experiment? I couldn't get that point.
No. In fact, I didn't know about the counterexamples. I did know that it was contested as to whether that was
Yeah. So that counterexample, that there was a PRL paper in 2011, and I myself have not followed the literature on that aspect since. So I was curious, since you picked up on that issue, that might be interesting to look at.
Right.
I also recall. I may send you that reference I have.
Yes, please do so.
Yes.
Very interesting.
So, and the last question just was that I want your comment that because those three experiments, if you compare them, those three loophole-free experiments of 2015, now one of them is there's about the 100% efficient event-ready detection, and the other two, the highly efficient photomultiplier. So in terms of application potentialities of this loophole-free test, so is the 100% efficient event ready better, or have already some applications based on that kind of thing done and compared with the other types? Means for say applications of the Bell's inequality in information theoretic context. So
yes,
has there been any development along that line?
So what I did see is that nowadays they are doing this with superconducting qubits, where well, they cannot get, I think the largest is something like 10 meters so far in was it Andreas Wallraff's lab, I think, where they also achieve much higher rates than with the NV centers, because that would certainly limit the applicability. You know, if you only have a few events per day, it would be very difficult to make a living out of that.
Yes.
On the other hand, the photonic experiments, I think they said and are trying to use these for certified randomness generation. Because basically operation of a loophole-free Bell experiment, if you take the measurement results, you sort of can be sure that it's random because you're violating the inequality. And I mean, this being NIST in Boulder is actually important to them. So I believe it might have an application, yes.
Okay. Thank you very much.
welcome.
So we have Lorenzo Macone, and then we have a question in the chat window.
I think the chat one was first. I'm not
Okay,
sure.
so then do you want to read that, Gregor? Because
Yes.
getting record, yeah.
As was said, there is a certain time interval between rotating the polarizer to detect different photons. Why is that a loophole in the locality? Can't we detect them anyway, including the time delay between the two positions of the polarizers? No, that you're correct. This is not a loophole. This is basically a question of, I don't have to use all the data. I can say, okay, during this time when I don't know what the state is, I will exclude detections. That's not a problem at all, because it's not the post selection based on the result. It's basically a time filtering, like you switch the experiment off for some time. So yes, thank you. And then I think Lorenzo.
Yeah, I was wondering, of course, except for conspiracies, what you did was to rule out the local hidden variables experimentally. So now that leaves you with two choices. Either you have non-local correlations, or can you make it local by some weird interpretation of quantum mechanics, like Everettian quantum mechanics, where maybe the detection events are stored in some memory which remains in a superposition always? Could that make the correlations local anyhow?
Well, that's so. I'm not really good on many world. I'm not really solid on many worlds. And
right, or maybe any other.
But one thing that you raise an important point, that is, people have been trying to exploit the so-called memory loophole, and that is the question of whether you allow, if you allow the hidden variables perhaps in your instruments to know what happened before, whether that poses a loophole for local hidden variables. And it turns out it does not. So it's been proven using martingales that also the sequence cannot be simulated. So even if you have memory in the system, but to make it physically local, I think there's just no way. I don't think so. So as an interpretation, I would say there is some non-locality. It's a very useless non-locality, because we cannot use it for much, but it's still, of course, so that I really have no idea how it works. Yeah, and even though I said, I'm kind of a believer, at the end, it leaves something to be desired. There's no question.
I agree with that. Thanks. Thank you for the nice talk. Yeah.
Welcome. Thank you.
Any Lorenzo again? A question or same hand?
Probably
same
still
hand.
the same.
No, I was lowering my hand. Sorry, something happened.
Yeah, I lowered it as well. So then we.
Okay. Sorry about that.
Is there any further questions for? Well, one obvious question is, what is the next obvious thing to do? I mean, experimentally.
Experimentally.
Yeah.
As I said, I mean, that's the problem. You and I know that precision experiments are a pain in a way.
Yes.
They have an advantage. You can keep doing them forever because you
can make them more and more precise.
Potentially more money and time to get one more digit of precision.
Yes.
And in the end, so. Well, I think the other thing is really, I mean, it's the applications, it's the QKD and so on. It seems to become really, I mean, quantum computing is one thing, but also I think in Europe right now there's quite a few things running on quantum communication. I don't know if it'll be really useful, but anyway, I like it.
Sure. Dipankar, that's a reference to the paper.
Yeah, that's a reference. Thanks. I'll copy that.
Yes, Sadiq, please.
Yeah. Hi. Sorry, my lighting is terrible. Right. So it was an excellent talk, and of course, you covered a whole bunch of historical progression. The thing is that all of this is So David Bohm in the 50s wrote these papers which set up, which formalized the hidden variable theories. Those are non-local, of course. But he also brought about, he wrote those motivated by the fact that, he wanted to point to certain uncomfortable truths about how the Copenhagen interpretation had been formulated and that it was non-falsifiable. So my question is that, are there efforts which can push using these technologies to kind of address some of the problems in the 50s papers of David Bohm?
Pooh. That I wouldn't know, I think. No, that's a bit too far from my, I'm probably not the right addressee. That, I mean, I've talked to many Bohmians, and as you know, we have there's a manifestly non-local hidden variable theory called Bohmian mechanics. I don't know if that's a satisfying solution. I don't think that interpretation-wise, of course, cubism has become very popular. I don't know if you would consider that a solution to the non-falsifiability of Copenhagen, but this is really a bit out of my depth here. There is one more question in the chat. Is there a bell-type inequality loophole-free experiment for the original EPR setup in position and momentum domain? That's actually a very good question. Yes, experiments have been done in the optical domain using sort of in the continuous variable language of quantum optics, where the field coordinates, so the electric field and magnetic field, or conjugate momenta, are the variables where then you can, in fact, talk about phase space representation and talk about quadrature measurements. I don't recall the reference though, but I'm pretty sure I had seen something, maybe some 2-3 years ago. I don't know if anyone can help me out here. Continuous variable Bell inequality.
So can I just interject here?
Sure.
Yeah, so aren't there reactor-based singlet decay experiments, the original EPR kind of experiments? I think they were done in the 60s, if I'm not mistaken, soon after
Yes,
Bell's inequality.
You're right. There was some. In fact, I've listed them in my thesis. There were some old experiments. The problem there being if it's some kind of gamma particles gamma photons that you measure, then the polarization resolution is very poor. I think more interesting in that respect are perhaps the BB bar and the K decay systems, and there is Beatrix Hiesmeyer. She's a physicist, theoretician, mostly in Vienna. She's been looking into these experiments and also trying to get the high energy physics community to do dedicated experiments on entanglement with their methods. Very often the measurement being the problem. So you have high efficiency, you can detect anything, but you have very, very poor sort of, for example, polarization or whatever the variable is. And in the K system, it's really the problem of there's the K long and the K short, and you basically, the particle chooses its own measurement. You don't get to say, I put my analyzer like this or like that. You basically have to live with whenever it decays, that's choosing the measurement basis. But there is always a bit of activity in that. There was a reference. Yes, for the continuous variable Bell test in 2010. Excellent, thank you. Well, in fact, I don't know if there are more questions. I should be conducting an exam soon here.
On Bell inequality.
Not on Bell inequality,
Okay.
but on quantum optics.
Sure, sure. So I
so-
don't see any. I think there is a question. Maybe we can treat that as the. Can you please highlight on the memory effect?
The memory effect loophole, yes. That is so what I know is that I would say that Richard Gill, I don't know if you know him, has sort of looked into how memory would, on the theory side, influence the derivation of Bell's inequality, because people have said you can sort of, this is a loophole in the derivation, and claims to have proven that it's not a loophole. Experimentally, I think no one has actually, I mean, how would you know about memory that you don't have access to? So I think that's not an experimental question, but more a theory question. You know, people have brought up various concerns as to why Bell's inequality cannot be constructed in the first place. It's the counterfactuality, it's absolute time variation, the non-existence of ensembles and whatnot. But none of these have actually, you know, many of these don't make a lot of sense to, as we as physicists trying to make sense out of data, if we can't look into correlation, if we have to assume that everything is new every time we look, then there's no point in doing physics. Yeah.
Sure. So I think, Gregor, so I don't see any other pressing questions. So I think we'll end the colloquium for now. So thanks a lot. That was a very engaging, very inspiring talk, and a great beginning to our online colloquium series. So thank you very much. And yeah, see you then. And thanks to everyone for also coming in. Bye.
Bye.